Equation of continuity. Mass of a moving fluid remains constant as it flows through a pipe where there is no sink or there is no source along its length. Then the mass entering the liquid fluid pipe will remain the same throughout its flow through the pipe. That means the mass of fluid entering the pipe from one end will be the same mass that will come out from the other end. This important observation, this important fact gives rise to a very important equation. That equation is known as equation of continuity. To understand this, let's consider this pipe. So let's consider a pipe of variable cross section. By variable cross section means its diameter is not same throughout. Let A1 be the cross-sectional area of the end through which an incompressible liquid is entering with velocity v1. Similarly, let A2 be the cross-sectional area of the other end through which liquid is coming out. With velocity v2. As the liquid is incompressible, so its density remain constant. So its density remain constant. If we consider that dm1 is the small amount of mass of the liquid entering through A1 in time dt and dm2 be the small amount of mass of liquid coming out of the other end of the pipe then if there is no sink and simply a small amount of mass of liquid coming out of the other end of the pipe in time dt, small time dt, then if there is no sink or source along the pipe length, then we can say that along the pipe, then if there is no sink or source along the pipe length, mass will be remain same. Mass of the fluid will remain same. That is, dm1 will be equal to dm2. So we know density is equal to mass by volume. So mass you can write as volume, density into volume. Now volume, as you can write, area into distance x. But wait, as it is traveling, as it is in motion, so velocity can also be written as x by t. That means in time tt, the distance covered by the fluid will be x would be equal to v into t. So that means we can write small mass can be written as rho a v into t, which I can also write in case of small amount rho a v dt. We can write like this. Therefore this is the mass which is entering. Therefore we can write here rho area 1 into v1 dt is equal to rho a2 v2 dt. So time being same, so as the liquid is incompressible, all the common factors get cancelled and we get here a1 v1 is equal to a2 v2. This is called equation of continuity. This relation is known as equation of continuity. Known as equation of continuity, and it is a very important expression, as it says how velocity of a liquid varies with the cross-sectional area, keeping the rate of flow of volume being constant. Okay, the term the product area into volume is expressed as like this, as dv by dt is equal to av. You can see it is the rate of change of volume. So we can call this volume, this relation is known as volume flow rate, or rate of flow of the volume of liquid. So the product AB is expressed as this and is known as, we can say like this, and is known as volume flow rate. You will see, because of this equation of continuity, we will see that when liquid enters through a large cross-sectional area and comes out enters with large cross-section area with a small velocity, but when it comes out from a small cross-sectional area, the velocity of the liquid increases very much. Example, in case of rivers, you will see the rivers where the river is very wide, there the velocity of the flow of the river is very slow. But consequently, if you compare this with the region where the river is very narrow, there the water flow is very high. This is because of the continuity equation, as the rate of change of flow or the volume flow rate is constant. So there's a variation will take place between the area and the velocity. If area is large, velocity will be less, and if the area is less, velocity would be large. If area is less, then velocity would be definitely large. and vice versa. So this equation explains the equation of continuity. We can see an example of equation of continuity question regarding this. For example, okay, before that, if the liquid is not incompressible, then if the liquid is not incompressible, if the liquid is not incompressible, then what will happen is the density will not be same. Then the density will not be same. It is compressible, means you can, when you're entering, it may get compressed. When coming out, it may not, it may get expanded, or it get less compressed. In that case, the density will not be constant. If the liquid is not compressible, then the equation of continuity can be written as like this. Rho 1 A1 V1 is equal to rho 2 A2 V2. This is for compressible liquids, where the density of the liquid can be compressed and the density can also vary. Now let us take an example to understand equation of quantity more properly. Let's say an incompressible oil of density 800 850 kg per meter cube is pumped through a pipe at the rate of 9.5 liter per second. So this is the volume flow rate per second. Determine the velocity of the fluid of the oil as it enters the pipe, if that section has a diameter of 8 cm. Also, determine the velocity of the oil as it comes out from the other end, where the diameter of the pipe is 4 centimeters. So let's see how to solve this problem. Let us first visualize the problem. So first is the visualization. So as we can read is that an incompressible means density is constant. Oil of density 850 kg per meter cube is pumped through a pipe at the rate of 9.5 liter per second. So that means we can draw a pipe here. It's a variable cross section because we can see the velocity of oil as it enters the pipe. If that section has a diameter of 8 cm, that means this is a variable cross section pipe. If the liquid is entering through here and is coming out from this side, the diameter in this situation, in this case the diameter is 8 cm, and in this case the diameter is 4 cm. So we need to find out with what velocity is the oil entering, and with what velocity is it coming out. Clearly we can see that this side the cross-sectional area is more, and this side the cross-sectional area is less. Definitely the velocity V1 will be less compared to the velocity V2, because that side cross-sectional area is less, so V2 will also be more. So in order to do that, let us see what is provided to us. First is the density of the oil. So density of the oil is 850 kg per meter cube. Then pumped through a pipe at the rate of 9.5, that means dV by dt, Q equal to dV by dt is equal to 9.5 into 10 to the power minus 3 meter cube per second. This is provided to us. Then determine the velocity of oil as it enters the pipe if the section has a diameter of 8 cm. Now diameter d is provided, which is 8 into 10 to the power minus 2 meter. Therefore we must write, so we need to find using equation of continuity. Using equation of continuity, we can write that dV by dt is equal to A1 into V1. So this is provided to us. We need to find V1. So V1 must be equal to dV by dt divided by area 1. So dV by dt will be 9.5 into 10 to the power minus 3 divided by area. Area should be pi into diameter. So diameter is given, that is it should be, radius would be 4 into 10 to the power minus 2. So 4 into 10 to the power minus 2 whole square. So if we solve this, we get this around, if I'm not mistaken, it should be around 2 meter per second. This is V1. I would like you to, I want you to please solve it on your own also and find out the exact value. I'm just approximating it to around 2 meter per second. Similarly, now for the other end. So for the other end, we're going to find out, now as we know this side, so for the other end, we can, using again equation of continuity, we can write now A1 V1 is equal to A2 V2. Now we need to find V2. So V2 must be equal to A1 V1 by A2. So in this case, it should be, area is pi into 4 into 10 to the power minus 2 whole square. This is the area of the first cross section, whole square into velocity that we have got around 2 divided by, this one will be, area should be pi into the radius. In this time it is given to as 4 centimeter, that is 2 centimeter now. So it will be 2 into 10 to the power minus 2 whole square. So on simplification, it should come near about to 8 meter per second. I just want you to do it and confirm. Maybe the numbers little bit here and there, but you can please do it the exact value, find out the exact value. Just to keep the video short, I am just writing the approximate value of the two values so that we can reach to the comparison. So clearly we can see V2 is greater than V1, and as proved, as derived, that where the cross sectional area is more, velocity of the liquid would be slow, and where the cross section area is small, the velocity of the liquid would be more. It is because the volume of the liquid flowing per unit time is constant and there is no sink, no source, so the mass entering the pipe and the mass coming out is remain same, and because of that only the variation in velocity takes place, keeping every other factor constant. So if area increases and V decreases, these things happens because of equation of continuity. I hope you all I've been able to explain it to you. This is a very important relation and it will help to understand the next important topic, that is called the Bernoulli's theorem. Thank you.